It's my pleasure to welcome Forrest Horton here as our colloquium speaker today. Forrest is an assistant scientist at Woods Hole Oceanographic Institution. And before being at WHOI, Forrest did his PhD at UC Santa Barbara with Brad Hacker and was a postdoc fellow at Caltech working on noble gases in olivine with Ken Farley. So Forrest, it says on Forrest's websites that he's a high temperature isotope geochemist, but Mike tells me that he has a long, illustrious career as a metamorphic petrologist before that. But Forrest has worked on all kinds of different topics, radiogenic heating in the crust, continental collision zones, and even geobiology, linking volcanic outputs to ocean chemistry. And he also has an amazing history of cool field work. So Forrest has been to the Arctic and Antarctica, Madagascar several times, Afghanistan, which we'll be talking about today, and both really far north and far south India. So I think Forrest has got a bit of time to talk after his talk for those who are interested, and that would be high on my list of things to ask him about. So today, Forrest is going to talk to us about a mysterious type of magmatism, the carbonatites. And in particular, he'll be talking about a carbonatite volcano in Afghanistan that provides a fortuitous window into the deep carbon cycle. So thanks very much, Forrest.
Thanks, Megan. It's great to be here remotely with you guys today. I'm really excited to talk about carbonatites. It's a topic that's excited me for a while, and the pandemic gave me a chance to compile some of the work that I'd done on that and think more about it. And I want to convince you that perhaps carbonatites play a greater role in the deep carbon cycle than we typically think. And I'll get into detail about why I think that might be possible, why that might be true. Oops, if I can go forward. So a considerable amount of thought has gone into the inputs and outputs of carbon into the deep Earth, and the dominant flux of carbon into Earth's interior happens at subduction zones, and carbon is released in arcs and continental rifts and ocean islands and mid-ocean ridges. A lot of effort has gone into quantifying these fluxes in recent years, and we have reason to believe that the fluxes have been balanced over geologic time because the climate has avoided hothouse and greenhouse, hothouse and coldhouse conditions for most of its past. Here's a figure from Planck and Manning, which compiles the major fluxes of carbon into Earth's interior and out. And in this case, the double bars are two different estimates, not two different fluxes. But the carbon going into subduction zones is not matched by the amount of carbon coming out of volcanic arcs. But some of that carbon is presumably mixed into the convecting mantle or enters the lithosphere, and then is released at mid-ocean ridges and in interplate settings. And I want to focus mostly on this sedimentary carbon flux into subduction zones, which is the greatest compared to altered oceanic crust and peridotite. And one way to quantify this sedimentary flux is to add up the amount of sediment on downgoing slabs, and these can be estimated by drill core and seismically. Here's a figure modified from Galvez 2020, showing the fraction of total sedimentary carbon per trench segment, and black it represents organic carbon and blue represents inorganic carbon. Note that the inorganic carbon is much larger, but what's important here is that the carbon inputs, sedimentary carbon inputs in particular, are highly variable along subduction zone segments. And I'm highlighting here with some stars some hotspots of sedimentary carbon inputs into subduction zones. And interestingly, the greatest fluxes of sedimentary carbon occur where submarine fans are being carried by subducting plates. And these, most notably, are the Indus Fan and the Bengal fan, both of which are produced by the erosion of the Himalayas. So if we look also at the carbon outputs in volcanic arcs, and here I'm showing a figure from IUPA 2019, the most modern estimates for carbon fluxes out of active volcanoes are from satellite measurements of sulfur, which are used then to infer the amount of CO2 emitted at these locations. And in this figure, the circles, the diameter of the circle corresponds with the size of the CO2 flux. What we can see is that the CO2 flux is highly variable across different volcanic arc segments. Comparing that to the sedimentary inputs, and I'm going to overlay here those hotspots that I noted in the previous figure. The highest sedimentary inputs, marked by the stars, are sometimes matched by high volcanic outputs, for example, in Sumatra and Java. In other cases, though, the high sedimentary inputs are not matched by volcanic outputs. In the Aegean, Macron, the Andaman Burma, and to a lesser extent in Alaska. So there's a lot of variability both in the inputs themselves and the efficiency of carbon return to Earth's surface. So if we look at a schematic that summarizes global fluxes in megatons per year, the input flux is about 80 megatons per year, and the arc volcanic output is only about 23. This implies that a great deal of the carbon entering subduction zones is either mixed back into the convecting mantle or returns and is stored in the lithospheric mantle. And this has remained controversial in recent years, and the two end-member views can actually be expressed or have been expressed in papers by Kellerman and Manning, who wrote, "We expect that little carbon is recycled into the convecting mantle." Hirschman in 2018, on the other hand, wrote that continental lithosphere accommodates only a small fraction of the carbon returned to the mantle. So theoretical and geochemical approaches to addressing this problem have arrived at very different answers. And I want to convince you today that carbonatites may provide some additional insights. Okay, so I'm going to turn to carbonatites now, which have been a classical problem in geology for some time. By definition, carbonatites are igneous rocks with greater than 50% carbonate minerals. This is a beautiful outcrop photo of the Alna complex in Sweden, and these textures are somewhat reminiscent of those that we might see in a silicate magmatic setting. And the dark here, which I'm outlining in red, are the remnants of a peroxenite dike that's been boudinaged and cross-cut by a later stage carbonatite dike. So these carbonatitic rocks, igneous limestones as they're originally known, have been controversial for at least 100 years, especially those in Sweden that were first characterized. In 1920, this Norwegian geologist, Brugger, published a memoir that's probably most notable for its lengthy discussion of carbonatites. And I actually think that he may have had time to write a 400-page memoir while he was under lockdown during the Spanish influenza outbreak in 1917, 1918. But in any case, he writes that the ultimate origin of the great mass of carbonatite rocks or carbonate rocks raises a question of great difficulty. It must be regarded as a primary magmatic rock. Its ultimate source must be a sedimentary limestone melted at great depth. And this is a translation. These were very controversial words. Another very well-known geologist, Norman Bowen, of the famous for the Bowen series, visited the same outcrops a couple years later and wrote that hot aqueous solutions had a profound effect on the igneous rock, causing carbonate replacement. In other words, he implied that these are not primary igneous rocks. He noted also that the fusion of a deep-seated mass of limestone is very unlikely in light of laboratory determinations. And what he means by this is that melting of calcite in the lab does not occur at temperatures below 1350 degrees C, which is excessively hot for the upper portions of the lithosphere. So this has been controversial for a long time. The origins of our modern view on carbonatites can be traced back to the very first paper in the very first issue of the Journal of Petrology by Peter Wiley. And Peter Wiley did these studies in the calcium CO2 H2O composition space. And I'm showing here only a very small fraction of the experiments he did. But he took calcite and added water to it. And what he found is that the addition of water, calcite will begin to melt at about 700 degrees C. And the amount of, or the temperature at which the calcite is entirely consumed, liquidus, depends highly on the amount of water. So these experiments confirm that igneous carbonatites are feasible at much lower temperatures than previously thought, at least by the initial researchers. And interestingly, they also affirm the suspicions of Norman Bowen in that aqueous fluids play a major role in carbonatite genesis. So we actually believe that small amounts of carbonatite melt may exist in the upper portions of the oxidized mantle, and for example, beneath mid-ocean spreading ridges, as a asthenosphere ascends, if it's carbonated, it will first melt in the carbonatite field, and these low-degree partial melts may ascend and be consumed by carbonated silicate magmas, or becoming entrained in the lower portions of the oceanic lithosphere. The vast majority of carbonatites on the surface, however, occur in continental settings, and I created this figure to classify all the different ways in which carbonatites might arise in continental settings. And the vast majority tend to be associated with continental rifts. And people believe that it's metasomatized regions of the lower lithosphere, carbonated by earlier melt or fluid events, may be reactivated and melted by heating during rifting. If this occurs, then small degrees of partial melt could produce primary carbonatites. Alternatively, and more likely in most cases, partial melting would produce carbonated silicate magma, which as it ascends, separates into two immiscible fluids, a carbonatite and an alkaline silicate magma, carbonatitic magma and alkaline silicate magma. And indeed, we often see alkaline silicate rocks associated with these carbonatites. Both of these mechanisms are viable for carbonatite production in ascending asthenosphere if it's carbonated. It's very difficult to tell the difference between these different scenarios at individual carbonatite localities. Okay, so there has been some exciting new isotope work done on carbonatites recently, and this study by Hewlett and others showed that boron isotopes record recycled subducted crustal components in carbonatites globally. More recently, Amsalem and others used calcium isotopes to suggest that carbonatites contain subducted recycled calcium. So this is an exciting new development, and one that I'm hoping to contribute to in this talk. If we look at this plot of primary igneous carbonatite locations globally, we see that there are carbonatites on every continent. We also can see that they tend to form clusters and are most concentrated in Proterozoic and Archean crust, shown here in dark blue and purple shades. Notable areas where carbonatites are abundant are in Canada, Western Greenland, Scandinavia, the Rift Valley in Africa, and in the southwestern part of Africa as well. My interest in carbonatites actually began when I had the unusual opportunity actually to visit this carbonatite volcano in Afghanistan. And this volcano is not associated with other carbonatitic rocks, unlike most carbonatites globally. But what was I doing there? I was actually working for the Department of Defense at the time with the USGS to identify mineral deposits that could be used by the Afghan government to produce revenue. And we were targeting the Khanneshin Carbonatite Volcano here in the Registan Desert and Helmand Province as a potential rare earth element deposit. Remarkably, Soviet geologists had mapped this volcano by hand in the 1970s, and even more remarkably, these maps were hid under the mattresses of Afghan geologists during the Taliban rule, probably under punishment of death, so that they could preserve them for future generations. They're still guarded by these Afghan scientists. So we use these maps to help inform where to go, and getting there was extremely difficult, even by geologist standards. We were able to fly in and access the volcano, shown here in a Google Earth satellite perspective, and it erupted very near the Helmand River and displaced it northward. The central vent, I'm highlighting here in red, is about 4 kilometers in diameter, and we were able to access the central vent along a couple of these drainages. We had to come in this behemoth of a helicopter, and we're surrounded by Marines who were very uninterested in geology, but it's a phenomenal site. Carbonatites are notorious for not being very well preserved, and as a young but inactive volcano, this is a very unique location. It's worth giving credit to the young woman geologist who ran this program, Emily Scott, who was my boss at the time. We came back with a number of hand samples, and the USGS has granted me access to those, and my results from them will be the main focus of this talk. So for the rest of the time, I want to talk about these Afghanistan carbonatites, and specifically I want to ask, where did they come from? And I want to also use the results of this study to talk or think a little bit about where carbonatites come from globally, and to bring it full circle, to think about what the implications for the deep carbon cycle are. So to give you a little more geologic context, this is a map produced by the USGS based on those Soviet maps that I showed, and the central vent is shown in the reddish hues, and the traverses that were made are shown here as these thin black lines. The structure is more easy to understand if we look at a cross section along this black transect here. The central vent is thought to have nearly vertical contacts with the surrounding wall rock. The volcano-sedimentary apron that extends many kilometers away from the central vent has been eroded along with the central vent, exposing the wall rock around the central part of the volcano. And the rocks here can be subdivided into four main lithologies. The wall rock is a neogene sandstone, mostly potassium feldspar. It's been brecciated and fractured. You can see the thin white calcite veins here in this image. The first eruptive episode formed the center of the main vent, and it's composed dominantly of calciocarbonatite. You can see the coarse grain calcium carbonate, and there are abundant wall rock xenoliths, which are micaceous, dominantly biotite fragments of altered wall rock that are seen in these units. And then subsequent eruptive episodes form these margins of the central vent, and they tend to be more ferromagnesian. Barite is a major mineral phase, along with calcium carbonate, anchorite, iron oxides. They tend to be darker in hand specimen. So what we were focusing on from an economic perspective were the subset of these ferromagnesian carbonatites that are very rich in rare earth element minerals. And in hand specimen, they tend to be yellow. And this is a sod surface of one of those rocks shown here. So the petrogenesis of these carbonatites can be understood by thinking about the rare earth element abundances. And I'm plotting here the calciocarbonatites in blue and the ferromagnesian carbonatites in red. You can see that in general, the ferromagnesian carbonatites, the later stage rocks, have higher lanthanum concentrations as well as other light rare earths. And there's some anomalies, but I think that the veins running through some of these earlier stage rocks may be transporting later stage elements into them. So this is actually a trend that's not unique to this carbonatite volcano, but seen globally. And it's a trend or the enrichment in rare earth elements in later stages of the eruption is typically attributed to fractional crystallization of calcite, in which rare earth elements are incompatible. So fractionation of calcite produces more or higher concentrations. However, this trend or this crystallization of calcite cannot explain the fractionation of light rare earth elements from heavy rare earth elements. And this corresponding trend is typically attributed to wall rock metasomatism that's going on during the eruption or magmatic differentiation. So this process was actually shown experimentally by Annenberg in 2020, who performed these experiments where the crystallization of calcite, shown here as purple, leaves a residual melt and at the same time, silicic wall rock is being modified by these residual fluids. The alkali elements are being deposited in these zones. Heavy rare earths are precipitated out, leaving a light rare earth rich marginal zone. So this is this general model fits the Afghanistan carbonatites very well. Now, to get back to the question of where did these carbonatites come from, I eventually decided to use the thallium isotope system with the assistance of Suna Nielsen here at WHOI. And the thallium isotope system is a stable isotope system with two isotopes, 205 and 203. It's typically expressed in the epsilon 205 thallium notation, where it's the 205 over 203 of the sample minus the 205, 203 ratio of a standard normalized to the standard and in per mil units. So this is a useful isotope system because it's thought to fractionate primarily in low temperature environments. So in marine sediments, such as iron manganese crusts and nodules, and in low temperature altered oceanic crust, there can be significant deviations from continental mid-ocean ridge basalt and depleted moor mantle values. And it's been used successfully in ocean island basalts to quantify the amount of recycled material that may cause this greater spread. Another draw is that the Khanneshin carbonatites are extremely thallium rich, so it made the column chemistry much easier and also improves our precision. But to skip right to the results, we found an enormous spread in thallium isotopic compositions, ranging from about -4 to about +4 in epsilon units. And this was very unexpected. We thought that there would be a nearly uniform composition, and we spent a lot of time trying to figure out why there might be such a large spread. And we asked ourselves, well, could magma heterogeneity be explaining this? And we don't think that that's a viable explanation, in part because the radiogenic isotopes are very uniform. We also asked ourselves whether contamination might be an issue, and we believe that we can rule this out because there are such high thallium concentrations in these magmas that it would take an enormous amount of assimilation, an unrealistic amount, to explain this much contamination isotopically. So we think we can rule out contamination. Degassing is actually a possibility. Thallium can behave as a volatile element in high temperature settings. And I don't have time to go into it, but we also have oxygen and carbon isotopic results that we think rule out degassing as a potential factor, leaving us with mineral fluid fractionation as a possible option. Not much is known about thallium fractionation in magmatic settings. This is actually one of the first studies. One previous study suggested that biotite can play an important role because thallium tends to behave like potassium in these systems. Well, we noticed a lot of biotite in these wall rock xenoliths, which leads us to speculate that perhaps this process that we're seeing that's enriching the light rare earths over the heavy rare earths is simultaneously fractionating the thallium isotopes. Specifically, the thallium 203 may be entering the potassic phases in the altered wall rock. Now, regardless of the actual mechanism of the fractionation, this is my summary slide of what we think is occurring based on these stable isotope results. And so we think that first there's a calciocarbonatite eruption, and as calcite is precipitating out, the residual fluids are driven to higher and higher iron and magnesium concentrations. while this is going on, immiscible fluids are interacting with the wall rock and driving the thallium isotopic composition to higher levels. It's very complex, but the more that I read about carbonatites, the more I realize they're enormously complex, especially in terms of the fluids, which I don't have time to go into too much today, unfortunately. But regardless of the exact explanation for the thallium isotopic fractionations, we're very confident that the primary magma had isotopically light values, and that some mechanism fractionated that in the volcanic setting. And this is an important realization because this is significantly lighter than average continental crust and the upper mantle, and it overlaps instead with marine sediments and altered oceanic crust. So what we concluded is that perhaps we're seeing a thallium isotopic signature of recycled seafloor. So with this in mind, I'd like to take a step back and think a little bit about the tectonic context, which I overlooked before. And the Khanneshin Volcano itself erupted here near the Helmand River, away from deformation associated with the India-Asia collision, and nearly 700 kilometers north of the Macron subduction zone. Now, the Macron subduction zone is unique in that it has the highest sediment flux per kilometer of trench of any subduction zone, probably. And this is because the Indus River is discharging water and sediments that produce an enormous Indus Fan that covers the Arabian Plate. And as this Arabian Plate enters the trench, it's a large fraction of it, a large fraction of the sediments are accreted, and this accretionary wedge is growing southward. Now, it's a very unusual subduction zone in this sense, compared to the ones we typically read about in textbooks. And I began asking myself, well, how far north does the slab actually extend? And we have some constraints from focal mechanisms of earthquakes, shown here as the yellow dots with their approximate depths in kilometers next to them. Interestingly, there was an earthquake that nucleated at 157 kilometers depth, not far from the Khanneshin volcano itself. So if we use these as a guide for slab top depths, we can contour them, create a depth contour here, which I've done in black dashed lines. And this suggests to me that the slab, despite being so far north of the actual trench, probably passes right underneath this volcano. And when I started reading more about the geology of Pakistan and Iran to the west, I realized that there are actually other volcanic centers associated with the Macron subduction zone. There are 3 active or recently active volcanic centers, and they fall on a linear trend that passes not too far south of the Khanneshin volcano. So I think that this suggests that spatially at least, Khanneshin volcanoes could be considered associated with the downgoing Arabian Plate. Okay, so to talk a little bit more about the Indus Fan, the Indus Fan covers the entire Arabian Plate, shown here, all the way down to the southern tip of India, and is multiple kilometers thick in many cases. Several drilling operations have recovered core from the fan, and there are two main lithologies in the Indus Fan sediments. There is a terrigenous turbidite component, which is essentially muds composed of material from the Indus Fan. And then there's a biogenic carbonate referred to in the core logs as fossiliferous ooze, which can constitute 50% or more of the Indus Fan in places. So it can be very carbonate rich. But importantly, the most of the trace elements in these sediments are hosted in the terrigenous turbidites, whereas most of the calcium and strontium and barium are hosted in the biogenic carbonates. So knowing this, I wanted to ask the question of whether the carbonatites, whether the trace element pattern of the carbonatites could be explained by melting of the Indus Fan material. And the Indus Fan can be approximated by this black line, and the Khanneshin carbonatite compositions are shaded in gray here, or the field that they produce is. So to approach this, I decided to make a two-stage model, and I used a study in which a metapolitic rock is melted to about 30 degree to produce about 30% melt, and this is meant to approximate the melting of the terrigenous turbidite component of the Indus Fan, which would have metamorphosed to a metapelite in the subduction zone. And what these experiments showed is that a melt that's produced from metapelites can have a trace element pattern shown in green here that's relatively similar to the rock that was melted, with the exception of the heavy rare earth elements and titanium, which are preserved in some of the residual mineral phases. So in this model, I'm assuming that the partial melt of the Indus Fan is has the composition of this green line. And then I used for the second stage, I used I assumed that this silicate melt became separated into a carbonatitic and a silicate magmatic fraction, and that the trace elements partitioned between those according to some experiments that were run by Martin in 2013. And without fiddling at all, I was able to reproduce trace element patterns very similar to those seen in the Afghanistan carbonatites. So this is by no means a unique solution, but I think that it demonstrates that it's plausible that subducted Indus Fan material can, if it's melted, produce carbonatites with this composition. Now, radiogenic isotopes can also be useful, and in particular, strontium isotopes and neodymium isotopes from Khanneshin Volcano, as well as those from the two other volcanoes in the Macron Arc, are useful. And if we look first at the mid-ocean ridge basalt field in neodymium and strontium isotope space, we see that it has a bit of a spread. And this spread is attributed to samarium neodymium and rubidium strontium elemental fractionation in a magmatic setting. But deviations from this magmatic fractionation trend are typically attributed to sediment recycling. The Khanneshin carbonatites fall well within this enriched mantle 2 field that's generally attributed to sediment recycling. So this is another piece of evidence suggesting that sediments played a role. To summarize, we have thallium isotopes, spatial associations with Macron subduction zone, trace element models that suggest that melting of the Indus Fan could produce these rocks, and radiogenic isotopes. And I'm inclined to say that we have a bona fide arc carbonatite volcano, and this is the first clearly identified arc carbonatite volcano to my knowledge. So this is an exciting discovery. So the age of the volcano actually wasn't known. It came through neogene sediments, so we assumed it was young. I had some, I did some argon geochronology on a couple of these phlogopite books found in some of the rocks. And what we found was that the argon ages range from about 3.8 to 3.5 million years ago. So this makes sense in light of the eruption through the neogene sediments. Now, and this is the interesting part, we can actually use strontium isotopes as a chronometer. And this is because marine carbonate is fairly homogeneous at a given time because strontium is well mixed in the oceans. So so we're actually able to produce strontium isotope records that go back hundreds of millions of years for marine carbonates. And this is shown here as this black line. So I measured the strontium isotopes in these Khanneshin carbonatites, and they have fairly uniform values that fall here. And fortuitously, their composition only overlaps with that of marine carbonates once in the last 200 million years. And because this is not old lithosphere, because there's no indication of local hotspot that could be contributing strontium, I think that we can zoom in on this overlapping isotopic composition here. So I'm inclined to believe that the Indus Fan material that was subducted into the Macron Trench had a deposition age of about 30 million years based on the strontium isotope compositions of the carbonatites. And because we have the argon dates for these rocks, we can constrain the recycling time scale to less than 30 million years, or about 27 million years. And this may sound like a long time, but it's actually much, much quicker than people have proposed that recycled material can end up in carbonatites. Previous studies suggest that it takes hundreds of millions of years or even billions of years for recycled material to erupt in carbonatites. So to summarize in one figure, I believe that the Indus Fan is entering the Macron Trench. Currently, it's entering at about 32 or 33 millimeters per year, and at that rate, even taking into account growth of the accretionary wedge, it would take about 17 million years to reach a depth beneath the Khanneshin Volcano. And at such depths, it's likely that mantle diapirs form because the sediments are so thick. Melting may also occur at the slab mantle interface. But in either case, was I muted? Okay. All right. I think everything's all right. In either case, as magmas ascend, they may differentiate into carbonatitic and silicate melt fractions, eventually producing the Khanneshin Volcano. And this time scale makes sense with the chronologic constraints that I just presented. It may have taken some number of years to enter the trench and then ascend, but the combined time from deposition to entering the trench and from release from the slab to eruption was probably less than 10 million years. Okay. So so I think it's helpful to compare the Macron subduction zone to subduction zones elsewhere. For example, in the Java and Sumatra segments of the, or subduction zone segments, there's very little sedimentary carbon entering the trench. Some is accreted. The altered oceanic crust component is poorly constrained. There's actually more volcanic CO2 coming out than there is sedimentary carbon entering the subduction zone. And this suggests that there's very little carbon entering the lithosphere, and there's very little carbon remaining to enter the convecting mantle. But if we compare this to the Macron, we see something very different. There's an enormous sedimentary carbon input, and as well as a fairly large sedimentary carbon accretion, but an extremely low volcanic arc output. Based on one study on one of the three Macron arc volcanoes, I was able to calculate a value of less than 0.01 gigatons per year. If we think about the Khanneshin Volcano compared to old Doino Lengai in Africa, we might be tempted to speculate that it could have produced less than 2.4 gigatons per year while it was active, but is no longer. So I think that the Khanneshin carbonatite is evidence that subducted carbon, sedimentary carbon, can be efficiently removed from the downgoing slab. And because carbonatites are so reactive with silicate wall rocks, it's likely that the vast majority that are released do not reach the surface. So the Khanneshin carbonatite is a rare expression of this deeper carbonatite process, I believe. Although we cannot, unfortunately, we cannot quantify the relative efficiency of carbon introduction back into the convecting mantle. If we think again about the ways in which carbonatites are generated globally, it's this mechanism of subduction zone carbon removal from the sediments is a viable mechanism for producing metasomatized and carbonated regions in the lithosphere. So these regions might be produced in rear arc or back arc settings when high sedimentary fluxes are present. And it's tempting for me to speculate that the clusters of carbonatites globally may represent lithospheric reservoirs that were once produced in these subduction zone settings. And I think it will be interesting to go out and try to evaluate some of these older carbonatite complexes in the context of paleosubduction. So to wrap things up, I hope that I've convinced you that the Khanneshin carbonatite volcano is part of the Macron volcanic arc, and that marine sediments can recycle into carbonatites on relatively short timescales. And I also have used this study to infer that sedimentary carbon can efficiently escape from subduction, subducting slabs in back arc settings. And it's tempting to speculate that lithospheric carbon reservoirs are produced by this process and may serve as source regions for carbonatites globally. So I'll leave it with that, and happy to take questions and stick around as long as people want to talk.
Thank you very much, Forrest. That was a fascinating talk. And I'm sure oh yeah, we've got questions coming already. Laurie, you were first up. Go ahead.
Hi, Forrest. Thank you. That was really, really interesting. I thought your strontium seawater curve matching was like so cool, but the one thing I didn't totally understand, like you matched your 87, 86 from the volcano to where it matches the sea level curve or the sea sediment signature, but wouldn't you expect like some mixing so that the 87, 86 you actually measure in the carbonatite wouldn't totally be from the sediment? I mean, I'm sure the strontium concentration is much higher in the sediment, but I'm assuming there's other inputs.
That's a good question. I haven't, maybe you're asking whether there's radiogenic ingrowth or whether there's ingrowth of strontium 87 in the rocks, and that's something that I haven't tried to quantify. I assume that there are weight percent strontium levels in these rocks, so I imagine that it's pretty trivial, but you're right, I should go back and calculate that to make sure. In terms of mixing, I'm not the way that I have justified using the strontium isotopes of the sediments directly is that biogenic carbonate is extremely strontium rich relative to most rock, which can explain why the strontium levels are so high in the carbonatites themselves. I think that it would take an enormous amount of contamination to influence the ratio significantly.
Okay, thank you. Yeah, I'm just not used to this rock type, so I wasn't sure. Thank you.
Thanks, Laurie. So the next question is from Will. Go ahead, Will.
Oh, thanks for a great talk, Forrest. I was wondering, so this idea of storing carbon in metasomatized lithosphere, I mean, is this something that we could verify by looking in the rock record? I mean, depending on how widespread it is, it seems like this is something that we should be able to see. Have you thought about that? Do you have, any targets in mind or evidence that you think you've seen of this kind of, large scale carbon storage via this mechanism? Well,
I mean, the lithospheric keels on the continents are very old and typically not exposed on Earth's surface. So there's not a great geologic record for looking at lithospheric mantle. Another problem is that carbonatitic rocks or carbonatitic magmas react very strongly with silicate rocks. And so it pressures beginning in the upper mantle and at crustal levels, they react to produce CO2. And so they basically dissolve CO2 and are no longer carbonatites. So the crustal record is very minimal, except in places where there are these volcanic complexes. But if you have any ideas, please let me know, because I'm excited about trying to look for them.
I mean, is this like, I often see like carbonatite metasomatism. People, they'll see like a weird composition and they're like, oh, it's like, must be carbonatite metasomatism. I mean, is that basically what we're talking about here? Is like, we're not really going to see any evidence other than some weird trace element compositions left behind in the rock? Is that kind of that's going to be the rock record of it, unless it's volumetrically high enough to leave behind actual, carbonatite, like in a volcano?
So it depends. I mean, I think it's hard to make generalizations unless we talk about a specific pressure and temperature range. It's possible that carbonate exists in the mantle as magnesite or dolomite, where the geotherms are cool enough that they can be stable. And so it's controversial because and one of the main controversies is over why the xenolith record globally has so little carbon in it. The xenoliths just, with some rare exceptions where there's magnesite, basically don't have any carbon in them. And so that's been used by people like Hirschman to say, well, actually the lithosphere doesn't have any carbon in it. Other people say that, well, there's going to be bias because carbonate minerals break down in magmas, silicic magmas, and we wouldn't see them anyway. So I'd say that the debate still ongoing.
Yeah. Cool, thanks.
Yeah.
Thanks, Will. And our next question is from Sarah.
Hi, Forrest. Really interesting talk. That's an amazing place that you've been working, and you've got a really fabulous set of observations and data, and I really like your story. It's really interesting. I'm curious about thallium isotopes because I don't know much about them. And you mentioned the possibility of them fractionating during fluid rock interaction in the I guess in the magma chamber or whatever with the xenoliths. And I'm wondering whether it's also a possibility that you would have isotopic fractionation of thallium during subduction, where you would actually alter the thallium isotopic composition. So that might be a partial or possible explanation for the low epsilon 205 thallium.
Absolutely. I think we're just beginning to learn more about the thallium, the mechanisms that fractionate thallium isotopes. I'm not. If Suna Nielsen were here, I would hand that one to him. But I think that most of the fractionation occurs in association with manganese, and so perhaps the breakdown of manganese phases or release of fluids that were potassic have the possibility of influencing the composition. Well, it's a good thought. We haven't spent too much time thinking about that. In fact, people had assumed until one previous study on silicic rocks and until this study that high temperature settings and subduction zones don't fractionate thallium isotopes, which is we're starting to think is untrue. So I'm not sure it is as good a recorder of subduction zone recycling as we thought. But I still think that in combination with all of the other observations we make, it makes sense.
Yeah, no, that's really interesting. Thank you.
Thanks, Sarah. And then we have a question from James. Go ahead, James.
Hey, Forrest. That was a great talk. So I have a question related to degassing, and you mentioned that you ruled it out based off of oxygen isotopes and carbon isotopes. And I guess I'm wondering if you could maybe expand on that a little bit. And then also I'm wondering whether carbon or oxygen isotopes are the best proxy for your system, and whether maybe you should be looking at other things like water contents in cerium or other tracers that help us identify degassing in more complex systems. Just because degassing is so dependent on so many different like pressure, temperature, FO2, and water contents, all these different things. And so I'm wondering if just simply relying on one system or two systems is the best, source of being able to rule it out. Do you have any thoughts on that?
No, it's great to see you again. That's a great question. I think that degassing is still a viable explanation for the fractionation that we see in the thallium system. I don't think it changes our conclusions in the sense that the primary magma probably had a isotopically light composition, but it could have fractionated the thallium to heavier values, and we don't have great constraints on that. I think, as I was mentioning before the talk, carbonatitic systems have mind-bogglingly high amounts of volatiles in them. It's not out of the realm of possibility that there was 28% water in these magmas before it was released, and possibly that much dissolved CO2. So, degassing is a major process, resulting in a major mass loss from the system. So I think that we really don't understand either the fractionation mechanisms for thallium or the degassing processes in carbonatite systems themselves. I think that I'm getting the sense that you have a much better ideas for how to constrain degassing. I'd be happy to work with you to come up with some ideas of how to test it. I've been trying to get you to analyze the sulfur isotopes in these rocks for some time now.
Yeah, I pretend like I know stuff, but I don't. But yeah, no, we should definitely talk more. When you have a little more time, I would definitely be interested in learning more about this system and how sulfur can help constrain, what's going on.
Yeah, no, I'm eager to get some sulfur data from these rocks. But let's talk sometime. Yeah. Oh, and I'm happy to talk about the carbon and oxygen isotopes if you want. It's a little bit of a longer conversation, but I'm happy to stay on after.
You don't have to do that today. We could and bore everyone, but we can chat, at another time, and you can talk about the fun stuff like the field work and that kind of thing.
Okay.
But thank you for going into that.
Well, if you have a minute, James Forrest will be still on the call once we've given him another round of applause. So thank you very much, Forrest. Let's give you another round.
Yeah. Great to see you remotely. I hope we can all meet up at conferences and so forth soon.